All right, we're back. We are on page 5 of Notes 2 of Calc AB, and we're using the chain rule to find some derivatives. And let's see if we can keep going. So I see here I have like an exponential function, which is kind of like the first time we've dealt with that. So you can do the thing where you break it down and you say that, y is equal to e to the u, and then u is equal to 5t squared plus sine of t. T, what is that? Let's go with, my T is a little weird there. T, there. Okay, I feel like that's better. And then what you're gonna do is we're looking for dy dx. So that's dy du times oh wait, we're looking for dy dt, not dy dx. dy dt will be dy du dt. So I could actually tell that I was wrong there because I wrote dy dx, and then like as I was writing down each of the individual derivatives, I was like, this isn't going to end at dx. So that has to happen though, right? We have to have it that, man, my voice is like scratchy today. We have to have it where, this and this will be the same, and then this and this will be the same, and then anything in between you have to have here and then up here. So like diagonals have to end up crossing out. Then you're left with the first thing on the top and the last thing on the bottom. And if you set it up that way, it's going to work. So the derivative, but then I prefer to do it a different way, right? I prefer to do it with an intuitive approach where I just say, I'm going to find dy dt, and it's going to be the derivative of e to the u, or e to the something, is just e to that thing. So e to the 5t squared plus sine of t times the derivative of that thing. The derivative of 5t squared is, so I'm going to go with parentheses here to make sure that everything gets multiplied by that e to the blah. So the derivative of 5t squared is 10t, and the derivative of sine is cosine. I wonder if this voice thing is allergies, which it definitely could be because every tree outside looks like it's just ready to explode with leaves. That's great because that'll be like a couple weeks of suffering for me. So we'll see. All right, same deal here, right? Derivative of natural log. We haven't really run into this yet with the chain rule, but we know the derivative of natural log, right? So we could say that y is equal to the natural log of u, and then that u is 5x squared plus 6. And then we're going to try to find dy dx. So dy dx is going to be dy du times du dx. Okay, but that's not my preferred way to do these, but you could do that if that's what you want to do. Not a problem. I prefer to think dy dx. All right. The derivative of the natural log of something is 1 over that thing. So it's going to be 1 over that thing times the derivative of that thing. The derivative of 5x squared plus 6 is just 10x. So usually what I do, I mean, we can simplify what we have there, but usually how I actually do these is I will, as I take the derivative, so we're going to end up with the same answer, but as I take the derivative, I just think it's like 1 over that thing. So what I'll do is I'll just make my division bar, fraction bar, my whatever. I'll do that. I'll put that in the denominator, and then I'll just in the numerator immediately put the derivative of whatever u was. So the derivative of u is 10x. You can't tell by looking at it which method I use there, but that's how I prefer to do it because it's just a little faster. You're just always skipping that one step. All right. Now this one's interesting because we don't really sort of know generally how to find the derivative of a base other than e, right? The natural log. So what we're going to do instead is change a base formula. So change a base. So let's say new color. Okay, the log of, let's say the log of b in base a, all right, a lot of dots there, is equal to the natural log of b divided by the natural log of a. Okay, that's the change of base formula. So You don't run into these often enough for this to be something that causes you any stress. But be aware, right? So when you're doing calculus, you need to be in radians because that's when the derivative of all the trig functions work out as nicely as we have them memorized. When you're doing calculus, you really need to be using base e, so you really need to be using natural logs. So step one here, we're not taking a derivative. We're just going to rewrite this as the natural log of the sine of 3x plus 2 over the natural log of 3, right? So we use the change of base formula. Now, what's kind of interesting about this, the natural log of 3 is a number, right? Like maybe you don't know what that number is as a decimal, but the natural log of 3 is just a number, like pi is a number, like 5 is a number, it's just a number. So this is actually, so I'm still not taking a derivative. It's actually 1 over the natural log of 3 and then times the natural log of sine of 3x plus 2. Now I'm going to take the derivative. 1 over the natural log of 3 is just a constant multiple, so it's just going to hang out. So dy dx is going to be, so 1 over the natural log of 3, constant multiple rule. And now what is the derivative of the natural log of something? So the derivative of natural log of something is 1 over that thing. So that'll be sine of 3x plus 2 times the derivative of that thing. What's the derivative of sine of 3x plus 2? Well, the derivative of sine of something is cosine of that thing. So we're going to get cosine of 3x times the derivative of that thing, right? So the derivative sine of something is cosine of something times the derivative of that thing. So the thing in question here is 3x. So the derivative of sine of 3x is going to be cosine of 3x times 3. And the 3 comes from the derivative of 3x. So I'm going to actually put it here because I feel like that makes the most sense. The derivative of 2 is 0. So first we use change of base. Then after we use the change of base, we just take the derivative of natural log. So you have to know the derivative of natural log, obviously. You have to know the change of base formula. It doesn't come up enough for it to be like, you know, an end of the world scenario for you. But that's how you're going to do it. So anytime it's not base E, anytime it's not a natural log, you're going to end up using that. All right, I'm going to do one more in this video and then come back in the next video and just keep going. So here, I think a good idea is to rewrite this as the quantity 9x plus 2 to the 1/6. All right, now we're just in a position where we're saying what's the derivative of something to the 1/6? So dy dx. So that's just power rule, right? So it's going to be 1/6 the quantity, which turns out to be 9x plus 2, but it's just 1/6 the quantity to the negative 5/6 times the derivative of the thing. So the thing in the middle there, the thing that we're composing is 9x plus 2. Its derivative is 9. So I think we should clean this up. So we'll say dy dx is 9 divided by 6 is 3/2. I'm going to leave it with the negative rational exponent because it doesn't really bother me. The only thing that you might want to do here is you might want to rewrite it. So I'll just do it. You might want to rewrite it like this. So 3 over 2, the quantity 9x plus 2 to the positive 5/6. Because now it's really obvious that x equals negative 2/9 is a 0 of the denominator. So it's not in the domain of the derivative, which means the derivative is undefined there. And negative 2/9 is in the domain of the original. So that's a critical point. Critical point at negative 9. Why can I not say that? Critical point at x equals, here we go. Let me just write it. So not a mandatory thing, but kind of the whole point of taking derivatives is to like use them, not just to go through the process. So I say critical point at x equals negative 2/9 because x equals negative 2/9 is in the domain of the function, but derivative is undefined. So these are like kind of, they're the rarer of the critical points. So I like to point them out when we get them so that you can like see like, yeah, they do happen. They're just not all that common. So this is a bunch of them. I'm gonna come back in the next video, finish this page, and hope you're finding these helpful, and I will see you there.